My first presentation, we're going to break them up. This one is on about winter probabilistic guidance. Point versus neighborhood is the main topic. And so what I'd like to show here is that maybe it's more probabilistic guidance, because when you look at the href, you're going to see some probabilistic stuff that says PMM, LPMM, and things like that. And so I want to explain how they get to that and what the difference is between point and neighborhood probabilities, because we know that finite and probably the best way to measure something is a point at the airport. But as we always, you always hear the folks on TV, well, no one lives at the airport. So we're going to talk about neighborhood probabilities some, and I hope everybody will be able to understand a little bit more. The outline, we're going to talk about the point and neighborhood probabilities. Then we'll talk about point probability. The neighborhood probability is called NMEP. You'll see that acronym through. The ensemble agreement scale, the EAS. What's the difference between those two? Probability match means, there's your PMM. And so then we'll just go ahead and start talking about the point versus neighborhood probability. Just remember, probability of event occurring at a specific location is a point probability, which everybody should know. We deal with that all the time in our guidance. Neighborhood probability, it uses multiple points with a radius of influence to calculate a probability. It used with a greater forecast uncertainty. We'll see, like in QPF, maybe a snowfall. There's more disagreement between ensemble models to a specific point, and it will be used in the ensemble approach. The neighborhood probabilities are low but are higher than point probabilities, and may be useful for decision support, and often used for smaller scale and rapidly evolving events. Now, here's a list of probabilities. We have location of an ASOS, a grid box in a forecast model, a small area of grid boxes defined by an area of influence. Maybe we want a probability at the Darlington Racetrack or at the Pecan Festival in Florence, a stream gauge along the Rockamore River, and maybe a slight risk of a tornadoes over eastern North Carolina. So I'd like someone to jump in here and tell me which ones are the point probabilities versus the neighborhood. Anybody want to try it? It's pretty easy.
I'll give a shot.
Okay.
One thing, they're all point except for the slight risk of tornadoes and the small area grid boxes.
Okay. Well, let's see what the answers are. You're right. Exactly. And so what you have to do is a combination. Let's say we have a slight risk of a tornado for South Carolina, but we want to know what's going to happen at the Darlington Raceway. So that's where you have to take into the account of what the neighborhood probability is with what you think it's actually going at the racetrack. And what's at the racetrack will be a lot lower than what would be in like the two-thirds of the state. For neighborhood probabilities, there's two approaches. There's an area influence, and I have my circles and squares backward here. But you see on the left, we have a square. This is more like a bunch of model grid points, and you can see that the center is here. And let's say this is 6 kilometers by, it's 5 by 5, so it's a 30-kilometer square. Or we can do a area influence as in a circle like we have here, and this would be typically used for like what's the probability of 50 dBz echo, and you can use that into your model so for a point. Now let's talk about the binary neighborhood probability. And what the binary probability here is this is the circle, the radius of influence here. Let's say it's 40 miles an hour, 40 kilometers, and we want 50 dBz echoes. And the blue in there shows where there's 50 dBz echoes that fall into that grid box. As you can see with the binary, if like here, there's nothing, that would be a no. There's a hit here, so that would be a yes, but there's only one of those 21 boxes. Notice here we have more. There's about 7 or 8 of those. But here you notice these are in partial boxes, but the center point's not there, so they do not count. So this would be a 0, and this would give us a hit. And since it says binary, it's either a yes or no question. It doesn't matter about the percentage. So if we go through here, we see yes, that has a probability of hit. That's no, yes, no, and yes. And so then the probability of the 50 dBs Z echoes of this ensemble, anybody want to take a guess what the probability of a 50 dB Z echo in this would be? How about 60%? 3 out of 5. That's pretty easy. Now let's look at one of the neighborhood probability example. Ensemble probability is used in discrete processes such as a meso-beta or smaller events. Classic convection, as we see in a CAM-allowing model for the href, where we get the href and its different members. In this example, there's a 40-kilometer radius, a circle there is, and we can see in panel C from the binary from the full set of ensemble members, we see where the hits are. 90% of those in that area are hit. So let's say there's 10 models, there'd be 9 that would hit with a 50 dBz or whatever value you have here. This is updraft helicity of a certain value. The maximum, or one that's greater than 75 meters squared per second squared with a radius of 40. So you can see here in the top right, this is our binary figure where we have the hits. So this is the top left is actually where the convection's going. If we did the binary technique, there's where we got that. And then down here, if we look at the neighborhood probability, which I'll show you how that's done, that is not through the binary as much as through a percentage. We'll see this is smoothed, and this is how they get the probabilities you see in the href for where we have updraft helicities greater than 70 meters squared per second squared. Example again of the this neighborhood operational guidance is the convective outlook. For this, the SPC uses a 25-mile radius of influence, and this would be for convective winds over 50 knots. Now, we're going to talk about the ensemble agreement scale, and this is exactly the same images that we had before, but here, instead of doing a binary yes or no, we are actually going to use an area influence using a fractional coverage. And this is a method to calculate the probabilities at a point using information with an area influence. So we look at the first one, and let's just go ahead and say that's 4 out of 21. The next one is no, none. The next one is 11 to 21. We have 0. And then we have 1 to 21. And then you just say, oh, that's one 19%, that one's 0, that one's 52%. These are all different members. That's 0 for that member and 5%. And then you just add those up and divide it by 5. And the fractional coverage there is 15%. That's how you would go if we went back with that 15%. And you can look here, if we have the yellow, that would be how they get that probability for SPC. Now let me continue here. Now, another problem we have is if there's orographic forced weather, which thank goodness we do not have it here, but I want to show you how the models handle that. As you can see here, Salt Lake City, and here's a grid point here, and we're using a 40-kilometer radius. But if you did a 40-kilometer, look at all this terrain here. If that would be force, maybe there's a flow from the west coming up here, or for snow, it would really smooth it out, and it would not show the fine detail due to the terrain. So what they do is they use the fractional coverage like we've used before, but what they do, instead of a 25-kilometer, they start with a 6-kilometer radius, and they continue to see each ensemble where it actually matches. And here we do have no similar criteria not achieved. And then the next one, what they do is they'll expand it out to 12-kilometer radius. see if they have a criteria. If it's achieved, then they'll calculate the probability. If it doesn't do it 12, they keep going out. In some places, on certain probability elements, they go out to 100 kilometers. So, for example, if we look at panel, what we have here is panel A is a point probability, B is a smooth point probability. Then we come back with the EAS technique, and this bottom right one actually shows what the radius is that's calculated. So what we see here is on the smooth probability, especially for California, you can see how, if you look at the, if people who've been out in California know California, the Sierra Mountains, and then if further up Cascades, there's no rain up there. If we look in this box here, you can see that here on the mountains there, it's only giving 40 to 50%. But if we use the EAS technique where it's looking at smaller radii and then building out the bigger ones, you can see actually it picks up the maximum here for the, the maximum here for the storm. And the radius, you can see the radius is here. You got some in the blue that are 10, and then farther out, it's 100, way out here off the ocean. But as you can see in the mountains here, the light blue is showing actually the 10-kilometer. So it is trying to pick up that resolution. Now, when do you use the NMEP or the EAS? Remember, the NMEP is fixed binary search. Neighborhood maximum is 0 to 100%. The EAS is variable fractional coverage, and it represents 0 to 100% based on the area influence around a point. Remember, the NMMP is a searching tool. How likely is an event to be nearby? It's useful for critical thresholds such as severe weather, heavy precipitation, or small-scale phenomena. The EAS is a smoothing tool. How likely is an event at a grid point? And each point with the search area is treated as an ensemble member. So that's the big difference there. Now here's an example of the two, and we look here at the NMEP for the precip. This is the California example, and you can see that, how likely is QPF over one inch. This could be snowfall also if you look in the HRF. Then we come back here and we're looking at the CCPA verify, and that is what the CCPA is, a climate for this type of event. This is what the 24-hour QPF should look like. But if we use the EAS that uses the radii that changes with size, you can notice here that it narrows down and shows stuff along the coast there in central and southern California, and then along the mountain range or Yosemite up into off Lake Tahoe, west of Reno, and then up into northern California. So that shows you some of the examples for that. Here's another example. This is organized precipitation, and this is where you have to be really careful on using this. The top left one is the NMEP for greater than 2 inches. And you can see the neighborhood. We have this big, large area from central Missouri up into Minnesota. We have some down in the Carolinas. And the ensemble agreement, which we start doing the radius, notice that it's really picking up the probabilities from Minnesota into central Missouri and over to Nebraska. But notice that it's only picking a little bit along the Gulf Coast and off the Carolina coast. And you can see the observed occurrence is greater than 2 inches. We see there's some here down in the Gulf where it had we saw there, but most of it is along the coast. And what that is showing most of this precipitation is, and we look at what date this is June 10th. This is unorganized summertime convection. So you have to be real careful when using this. You would want to use the neighborhood in the summer for us versus what you would see in the EAS. It wouldn't show anything. So there's an example when to use one and when not to use one. And we'll keep going there. Now, one of the problems is when you do all these techniques, you actually smooth it out and we lose the maximum probability or maximum value. And so what they've come up with is a maximum probability matched mean. And we'll see that in the HREF you'll see that drop down. And the purpose is to correct for low biases of the peak values and to maintain a spatial distribution in the ensemble mean and retain the peak values of the individual members. And here's a simple example. Here we have the hurricane that's coming up this last year, coming up into the Alabama, Gulf Shores area over into Mississippi. A simple example, let's say we have 4 grid cells with 5 ensemble means. For a grid cell 2, let's say this is 1, 2, and this is 3. For grid cell 3, you notice it's 3, 5, 7, 9, 11. And a classic, you would just add those up, divide by 5. So the max value in grid 3 here is 7 inches versus 3, 6, and 8 in the other ones. So that's a traditional ensemble mean. Now, we sort the values of the ensemble mean from the lowest to the highest, storing the rank and location of each value. So if we noticed here before, this is exactly what we had in the previous example. Now what we do is going from lowest to highest, we take every value from every grid, all five values from each grid point, and we put them from the highest to lowest. Then because we know there's 5 ensemble members, we select every nth element or number, which is the number of members in the, if we had 90, it would be every 90th value or 100th, so forth, but this we had 5. And what we do is we take the 5th value of each one, 3, 6, 8, and 11, and then we assign those to those grids, as you can see there. And so what happens, the grid point is replaced by highest value in the distribution. And it limits, and what's good about this is it limits the domain to a small area. And in this example, as you see down here with the hurricane that's coming in, and then the low, almost kind of a boundary, a warm, pseudo warm front over here, and then there's some convection down off the big south tip of Texas. And what we see is we reduce the chances of QPF from one coherent precipitation. And if you look here to into these values here to the right, notice that this technique will actually break this into 3. So a max value in B would not influence a max value in A. So what we have is the top left is the ensemble mean. We have the probability match mean, PMM, which we noticed. And notice here the max here on these. The bottom left is the ensemble maximum of the storm. And then if we do the probabilistic match means, which is the local one, which we see there, which is that technique we use, can you see the peak values and the maximum values are kept for this convection off the Carolina coast and also down to South Texas. And the key there is it tries to keep the influence of max, like here the hurricane, let's say it had 20 inches or something there, it wouldn't influence something that's over in the Maryland or whatever. We wouldn't want to do that because that would be totally separate type of cause for that convection. So here's, you can see here again, this is the ensemble. We have a value here 15, but if we do the ensemble maximum from the 10th percentile, you can see we have over 20 inches. The mean, of course, smooths it out. But then we come with the probabilistic match. We do have, remember how big this area was here at South Alabama, 20 inches? Well, the probabilistic max is smaller here. And you notice here the convection off the Carolina coast, you can see the maximum is a little bit closer. The other thing, notice how even though it's local versus max, the area of the size of the 20 is not smeared or expanded or smaller. So that's what those values mean. And I was going to show an example of QPF example from the HREF. As you can see here, as you drop down, this is the winter section. And you can, when you talk about these PMMs and LPMs, if you notice here, we have the PMM values for 12-inch snowfall. You have threshold values and so forth. And if you look here, here's the PMM match along the Cascades here in Washington. You can see that nice max there. And then here's the precipitation, which we're also using for the problem match. You can see how the precipitation, and look at the nice detail of the precipitation amounts that are coming out compared if we use the just regular binary. So I just want to show that. That's all I have, and I just wanted you to get a basics about what's causing this and how it's actually created, and know which one to use in the right scenario. So if there's any questions, go ahead. If you're asleep, wake up. And any questions?
Not a question, but just a comment. I wanted to say I've had a lot of success using the PMM 3-hour QPF from the HREF site for timing the onset of precipitation before.
Ah, excellent, excellent. And one thing you can do, it will also help in your decision support. Are you coming up with a max QPF? Right now, I guess the QPF product will have it, but for DSS, you can definitely use that LPMM, the locally probably matched mean, to help you, communicate what you expect, and it won't be overblown from the hurricane. There's no other questions. I guess it's a break time, right?
Yeah, and I will say that the like on CLC, there's the foundations and probabilistic forecasting that explains a lot of this, along with like other statistical stuff. And it's things like an hour, or it's a couple hour course, but it's well worth it.
Yeah, and that's where all this came from.
Yeah. So if anyone wants a refresher or some more, it's got a lot of good stuff in it. But yeah,
Exactly.
I recognize a lot of those examples from the training.
And this is very, very important, guys, because for you, they're going to be around another 20, 25 years. This is going to become very important for your interpretation and for decision support services.